Hello, welcome again. We are covering the topic axial flow compressor for civil services MECH, IFS and GATE aerospace exam. And the next subtopic in the main topic of axial flow compressor is your elementary theory. So to discuss the elementary theory, we will consider this diagram first. So this is a single stage of your axial flow compressor. One is the condition of air at inlet. Two is the condition of air at the outlet of rotor, and three and this is your stator, and three is the condition at the outlet of stator. Okay. So at point 1 the pressure is P1 and temperature is T1 and velocity is C1. So or we can say this is your dynamic temperature at the inlet. So this is your stagnation condition. So T01 is the stagnation condition and T01 is the stagnation condition. And in the rotor some energy is imparted to the air, so the stagnation temperature would increase, so it becomes T02 and the pressure becomes T02. And this is the actual condition of air at point 2 or at the exit of rotor. So here the temperature is T2 and pressure is T2. Okay. And in stator no further energy is imparted to the fluid, only the kinetic energy is changed to pressure energy, and in that case there is some pressure loss also. So here this is the stagnation temperature and stagnation condition at the exit of rotor. So there will be some pressure loss in the stator. That pressure is here P03, so P02 minus P03. Okay. But the stagnation temperature will remain same because no energy is imparted in the stator. If C2 is the velocity at the rotor exit, then this is the dynamic temperature at the rotor exit, and from the stagnation condition we can obtain this actual condition. And if C3 is the velocity at the exit of stator, then this is the dynamic temperature at the exit of stator, and this is your stagnation condition, and this is your static condition. So this is the explanation of the diagram of the stator, of the axial flow compressor. Now I will read this and explain if needed to explain. A sketch of a typical stage is shown in figure. Applying the steady flow energy equation to the rotor and recognizing that the process can be assumed to be adiabatic. Adiabatic means no heat transfer is taking place, okay, but work transfer is taking place. It can be readily seen that the power input is given by, so here we can see that the final stagnation temperature is your T02 and initial stagnation temperature is T01. So the power or the work done per second is your mCp T02 minus T01. M is mass for it. So this is your work done. So this is equation number 1. So this is the work done per second or power input in the rotor part, and this is the stagnation temperature rise, and this is mass for it, and this is Cp. In the stator part there is no stagnation temperature rise. T02 is equal to T03. In the stator the process can again be assumed adiabatic. The process can be assumed adiabatic because no heat transfer is also taking place, and there is no work also, and there is zero work input. It follows that stagnation temperature will remain constant. So here between 2 and 3 the stagnation temperature will remain constant. Okay, so T02 is equal to T03. All the power of is absorbed in the rotor and stator, merely transform the kinetic energy to increase in static pressure. with stagnation temperature remaining constant. So no power is delivered in the stator, so it just changes the kinetic energy into to your heat energy uh, or into pressure energy. Next is next part is the increase in stagnation pressure is accomplished wholly with the rotor. Stagnation pressure will rise in only in the rotor, and in practice there will be some decrease in stagnation pressure in the stator due to fluid friction. Losses will also occur in the rotor, and stagnation price will be less than would be obtained with an isentropic compression and the same power input. So, due to losses, the stagnation temperature, stagnation pressure rise would not be as much as that would be obtained uh, by isentropic compression. Okay. So, ideally, the stagnation pressure rise would be uh, more if uh, we consider isentropic process, but we are getting here the stagnation pressure rise P02 minus P01, and there is loss in this part also. That loss is your P02 minus P03. So this is the explanation of this diagram. And in the next video we will study the velocity diagram of the axial flow compressor.